Hey everybody, my name is Mark. Welcome to. So basically, I did the meta career questions. I did the level one ones almost. I think I have two left. So I just wanted to go over the ones that I did today and see if uh, if I can explain them well. So let's start with the first one. It's called cafeteria. A cafeteria table consists of a row of n seats numbered from 1 to n from left to right. Social distancing guidelines require that every diner be seated such that K seats to their left and K seats to their right, or all the remaining seats to the side, if there are fewer than K, remain empty. There are currently M diners seated at the table, the ith of whom is in seat SI. No two diners are sitting in the same seat, and the social distancing guidelines are satisfied. Determine the maximum number of additional diners who can potentially sit at the table without social distancing guidelines being violated for any new or existing diners, assuming that the existing diners cannot move, and that the additional diners will cooperate to maximize how many of them can sit down. So let's take a look at the example. So here we have n equals 10. So let me switch to this. Okay, so here we have, let's see, n, let me switch to my pen. Okay, we have n equals 10. And then, oh, where did that go? There it is. Okay. Easy. N equals 10. And then we have k equals 1. K equals 1. And then we have m equals 2. Forget what all these letters are. And then s equals 2 to 6. 2, 6. So there are 10 seats available. And it's actually, this is one thing that I got caught on. It starts at 1. So here are seats 1, 2, 3, 4. I mean, the comma's to 10. And so then we have somebody sitting here. Let me just put like a chair here. And then we have someone sitting here. So what is K again? Let me see. K is, the number of social distancing seats. And what is M? Currently M diners seated at the table. So M, I mean, we can pretty much ignore this since M is equal to the length of S. And I'm sure this matters in like C or something when you don't really know the length of S, but here it's Python, so we know the length of S. So who gives a crap about M? So here we have our two people who are sitting down, and we want to find out how many more diners we can put in here. So let me remove the dot dots. Let me here. Actually, you know what? I'll draw it here. So let's just say this is square 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, that is 9. And then here we have 10. Okay, so somebody is sitting at 2. Right here, this is taken. And then somebody 1, 2, 3, 4, 5, 6. Somebody sitting here. Okay, so the distance between people should be 1. So if we look here, we can add someone here because there's an empty spot here and an empty spot here that's not being violated. And we can also add someone here, and we can also add someone here. So it turns out that the optimal strategy, I mean, this is a pretty simple problem, but it's sort of greedy. So the moment we see an empty seat, so it's like the question is, okay, we have these two people sitting here. So what is the maximum number of people? So first of all, if we put people inside here between these two, it's not going to affect anybody on the outside, right? We agree with that. So number one. So second of all, if you put people in here, starting from the left. So let's just say, for example, instead, don't do that. So let's say instead we had like, instead we have like a ton of chairs between these two people. So I think the greedy solution of just counting. So here we have K empty spots, and then we plop someone down. So here's our new, I'll just say like our new attendee. And then we go another K empty spots. And then we plop someone, because we can't move this one and we can't move this guy. So the best we can do is start from the beginning, go forward K empty spots, plop someone down, go another K empty spots, plop someone down, and go on. And this sort of greedy solution of just putting in one as soon as we can, this is the optimal solution. Optimal. This is totally optimal. So So then, yeah, so I think this helps solve the problem a lot. So if we can keep going with the problem, I noticed I was also caught up on this. So the S is given as this S26 like this. It's not, so I originally thought that it might have been given like this, like an array. So 0, 0, or not 0, 0, it's 0, 1, 0, 0, but this is not the way. Dot, dot, dot. This is not the format it's given. It's given as 2, 6. So these are the people that are sitting down. So here, let's try to think of, so we came up with this optimal greedy solution. So then let's look at how we can leverage this into a coding solution. So we could, of course, do, this is my original solution. So we take this 2, for example. So here we start at 2, and then we hop forward k plus 1 spots. So k in this case is 1. So we hop forward 2 spots, and we go to 4. And then we hop forward again. We make sure that 4 is far enough from 6. Far enough from 6. Because if it's too close to, if this 6 were instead 5, then we can't put somebody at 4, right? It has to be at least 1. There has to be at least one position away from the end. So we hop forward k plus 1, and then we hop forward k plus 1 again, and see if it's still not close enough to 6. So we keep doing this until we reach 6. At that point, you know, that's the end of this one. And if this S were longer, if we had like 2, 6, 10, or 15, whatever, then we would do this thing again. So we grab 2 numbers and we hop between them to see if we can stick any number of people between the 2 and the 6, or the numbers. However, this is slightly inefficient because you have to do a loop between the 2 and the 6. And let me just give you an example of when this is going to be super slow. So let's just say we have somebody sitting at, position 0. This, again, it caught me up. So imagine we have somebody sitting at the first position, which is position 1, and somebody sitting at the position, a really, really, really large number. So then, in our solution, what we're going to do is we're going to start at 1, and let's just say k equals 1. So then we're going to hop forward, we're going to hop to 3, and then we're going to hop to 5, and then we're going to hop to 7, and then we're going to hop to 9. And each of these places are a place where we can insert an additional diner. And we're just going to keep on doing this until we hit like this really huge number. But this is super inefficient. Why? Because what we really can do is we know, so first of all, okay, I forgot to mention. So this is what I assumed in the problem statement, that this S was sorted given that the numbers are 2, 6, but it's actually not sorted. So it could have been 6, 2. So in order to, for my convenience, I think this is probably optimal. I don't think, so sorting is an n log n operation. And I think we probably do have to sort. I don't know if there's a better solution online. I don't think there's any solution without sorting. We probably have to sort. I think it's unavoidable. Probably have to sort. So if we're going through these numbers in pairs, like let's say 2, 10, 20, 35, like this. So here's our, so I was telling you about this example, right? Where we have, we don't want to hop. We automatically know that the best way to solve this is like, the question is, how many people can we fit between 1 and this huge number? Well, given that we know that the list is sorted, then we can fit in people at 3, 5, 7, 9 like this, because we know it's sorted. There's not going to be any other people that are already sitting in between these 2 people. So what we're going to do is we're going to take this really huge number, the end, and then we're going to subtract the start. And then we're going to integer divide this by whatever it is, k plus 1, probably. So this is 2. So the idea is we're going to see how many people we can stick in here, and then we're probably going to subtract 2 or something to make it work out. So let me give you an example. So in our example, if we have somebody sitting at 2 and then we have somebody at 6, we subtract 6 and 2, we get 4. Then we integer divide. We integer divide by 2, which is k plus 1. And we get 2. And then we have to, just to make it work out, subtract 1, and we end up with 1. And that's the number of people we can fit in between 2 and 6, which is this one person at 4. So yeah, let me go over the algorithm again. So here we're given our list, 2, 10, 20, 35, and we're just going to look at these numbers in pairs. So we start out with looking at 10, 2. So we subtract 10 and 2 to find out the distance between them. So that's 8. And then we integer divide by k plus 1, which is 2, and we get 4. And then we subtract 1, and that's 3, and that means we can fit in 3 people between 2 and 10, which is at positions 4, 6, and 8. Okay? And then we keep doing that for the rest of them. So this is, we fit 3 people in here, and then we fit some number of people between 10 and 20, and then we add all these up, and at the end we get our final answer, which is the total number of people we can fit in between 220, 1020, 20, and 35. However, we also do need to take into account the people that we can fit in before the first guy who's sitting down and after the guy who's sitting down at the end. So the cleanest way to do this is to add sentinel nodes. Now, sentinel nodes are kind of complicated, but basically we're going to add like fake people who are sitting down in order to, so if I add a fake person at 1 minus, I think, k, let me check. So there's my solution. No, 1 minus k minus 1 minus k minus 1 like this. And then we add a fake person at n plus k plus 1. So then, so let's just say k equals 1. And then here we have our positions. Let's just go to 5. So let's say n equals 5. And then this is the first possible place that somebody can sit down. Then the sentinel node that I just added is at 0. No, it's at -1, right? 1. Did I do that right? 1 minus k minus 1. So there is a parentheses here. So k equals 1. So we subtract. So the person I just added is sitting at a fake spot called -1. So what does this mean? This means that we're gonna when we're gonna look at pairs of numbers here, the first pair of number. So this -1 is added to this list. So instead the list looks like this: -1, 2, 10, 20, 35. I mean, there's only 5 spots. So let's say -2. I don't know, here, like that. I mean, okay. So let me rewrite it. So let's just say there's somebody sitting at 2 and somebody sitting at 4, and we're going to add in this fake spot -1. Let me cross this out, and we're going to add this fake spot n plus k plus 1 is 7. Yep. So somebody is sitting. So we added this fake person that's sitting at -1. So when we look at pairs of numbers, the first pair of number we'll look at is 2 and -1. So if we put someone at -1, we can still, I mean, if there wasn't somebody sitting at 2, we could still put someone at 1. Why? Because the distance between 1 and -1 is, there is k spots between them. And this means that if there wasn't a 2, we could put somebody at 1. And this kind of helps make the pairs of numbers clear, because instead of like having a special case for the beginning, we can just add this like extra node in the beginning, the -1, which makes the math easier. So we can treat the entire list as just we grab pairs of numbers and that's it. And the same thing, we can add a fake person who's sitting here. So I mean, this is the bounds of our problem, 1 to 5, but we added a fake person here so that we can put somebody at 5 without a problem. And like this, the math of like finding the distance between people, like for example, if we wanted to find if there were no people sitting down, and or let's just say there's somebody sitting down at 3, so 3 is in our list, and then we add the 7 in. So we can do this math where we did the 7 minus 3 equals 4, integer divided by 2, this is equal to 2, minus 1 is 1, and we can add somebody at 5. Right, so we can treat the 7 as somebody who's sitting, like a ghost who's sitting here, and it makes our math easier because we do end up considering this 5 when we do our calculation, when we go through pairs of numbers. Hopefully that makes sense. So yeah, so this is exactly what I was talking about. We go through the pairs of numbers. Oh my god, what happened to my... There it is. We go through pairs of numbers, we integer divide by k plus 1, we subtract 1, and then we add. So that's a possibility that of somebody that we can sit down, and then we return the sum of all of those. So let's go to the next problem now. Scoreboard inference. Did I do this? I guess I didn't do this because it sent me to the problem which I could already do. So let me go to director of photography. So this was kind of difficult, and I think there's a part 2 which is more difficult. So I'm just going to tell you how I solved it, and it might not be the optimal solution, but let's just go for it. So let me down. So so the main centerpiece of this problem, we're given a string of either dot, which is an empty space. So let me say empty, and then we have P, which is a photographer. So he's the one taking the photo. And then we have the actor, which is an A. And then we have a backdrop. Backdrop. So then we're looking, so we have a string of these numbers, like for example, let me give you an example. Let me do the last one. P, so there's a dot, P, B, A, P, dot B. And we're trying to find something called an artistic photograph. So what is an artistic photograph? An artistic photograph is number one. We have a P, and then we have an A. So we have a photographer taking a picture of an actor, and then there's a backdrop. Okay, or we could have a backdrop. So it could be in the opposite direction as well. That's okay too. Like the photographer is taking a picture of it. Like the photographer is taking a picture this way, you know, taking a picture of the actor, which is in front of a backdrop. But the second condition for being an artistic photograph is that the distance between P and A is less than or equal to x, and greater than or less than or equal to y, and greater than or equal to x. So what does this mean? If x is like 1, and I should also say, sorry, distance between P and A, and also the same thing applies to A and B. So what does this mean? This means that if we have our P here, and x is equal to 1 and y is equal to 2, then the distance between P and the A, the distance can be at most 2. So he can't be outside. The actor can't be too far away, and it also can't be too close by. I mean, in this case, x is equal to 1, so he can be right next to him. But if x were like not equal to 1, then the actor can't be that close. And the same thing, so the same condition is applied to the x and the y are the same both for the P and A and the A and B. So the same condition is applied to at most 2 between the A and the B. So, so here we have our string right here. So let's take a look at some of the artistic photographs that are possible here. So we have the dot, and then we have, let's see, so here's our P, right? And there's one distance between this P and A, and that's okay. So we're just gonna put a tilde there to show that there's something there, but we don't really care. So there's our actor, and the distance between these two is at most 2. So x, in this case, x is equal to 1 and y equals 2. So this is fine. This is a good distance. This works fine for us. Good distance. However, there's no b. The next b is really, really far away, which is, it's greater than y. So this is not an artistic photograph. It's not possible. If we choose this photograph, this P here, and also any other A. So as you can see, we pick at a P, we're trying to find an A that fits for it, and then in addition, we're trying to find a B that works for that A, right? So a B might work for one A, but not for the other A. So in this case, we pick this P, we try to look for an A that works. There's only one A that works, it's this one. And then we try to look for a B that works, but this B is way too far away, so that's not gonna work. So then let's look at it from the back side. So if we look at it from the back side, here's our P over here. This is the P that I'm referring to. So there's an A right here, and that's fine. It's between 1 and 2 tiles away. 1 meaning it's right next to it, and then there's a B right here, which is 2 tiles away. There's something here which is an A, but it doesn't matter. So this is a good artistic photograph, and there's another good artistic photograph if we instead choose the same P and then choose this A, and then choose this B here, this is also good. So the number of artistic photographs here is it 2? Did I make a mistake? I, P, B, A, A, P, B, A, A, P. Interesting. P, A. It looks like I did make a mistake. So this first part, there's actually an artistic photograph here. So this P, and yeah, so this 2 distance away. So this is that 2 distance away? Yeah, that's okay. It's about the number of people between, so that's okay. So there's 2 people in between. So then we have an A, and then there's 2 people between that and the next B. So this is also an artistic photograph. So there are 3 artistic photographs here. Photographs. So I don't know if my solution is optimal. It probably isn't. But here are some things I noticed about the problem. First of all, if you go forward, so you can, so this, like solving the problem forward, forward and backward is the same. So you can just reverse the list. You can reverse the list. However, I don't think you can use, I think you do have to go through the effort of going forward and backward. Have to go through effort. Like there's no trick of like solving both at the same time of, looking forward. So the thing that I was doing here, right, is I first looked forward to see, oh, if we pick a P and then we look for an A to the right and then a B to the right of that, then can we find something that works? And then I went backwards, right? If I start from the end and I find a P, can I find an A to the left and a B to the right? So I don't think you can solve both forward and backward at the same time. What you can do is, they are symmetric. You can solve it forward and then you can flip the string and solve it backward. So that is something which I think is probably true. Number 2. Yeah, so there is the other thing that I noticed is that you can optimize some of the workouts. Let me give you an example. So if I have a P here, and then I have a P here, and then I have an A here, and then I have a B here, and then I have a B here. The X and Y can be really huge and a really huge distance, which means this searching that you need to do has to be really optimal. Searching probably should be optimal, or should be really quick. So if we're looking left to right for now, so this is the first step, and we choose this P. So then we're looking for A's. So here we found an A. And then from this A, right, we need to find some B's that work in our X and Y. So here, maybe this one doesn't work, but then maybe this one works. So we just did this searching, right, where we started at P, we found an A that works. So I think it is unavoidable. I don't think there's a way to do this. I think we do need to, if we start at P, we do need to look for every single P. We need to try to find which A's work. So if we find a P, we need to find which A's work. That's something which I think is true. So that's unavoidable. However, this is the work that we can optimize. Work that's optimizable. So if we found this A, then after this A, we look for B's that work, that are between X and Y. So here we find, let's just say, the number of B's that work. So then in the next step, when we start looking instead at this P, then when we start looking at second P, suppose that the same A works. It fits between x and y. Same A works. So then what I'm trying to argue here is that we can use the result of this previous computation to find the number of B's that worked in this A. So this A nothing's changed about this A, right? So in this previous step, we found the number of B's that work for this A that are between X and Y and that are actually B's. We had to go through the string and like loop and try to see how many B's work for this one. So now that we're on this P and we're okay choosing this A, there is the same number of B's work. Nothing has been moved around. So we can reuse the computation that we used for this P. We can reuse it in this computation. So what I'm suggesting is that we keep a dictionary. So here's our dictionary, or a hash map of so assuming we found an A, so let's just say the position of this A is I equals 2. So we keep a hash map between the position of an A, so 2, and how many B's, number of B's that work. So we can reuse that work. So in this case, it would be 2 if that's as big and both of those B's work. Or no, actually I crossed one out, so this will be 1. So therefore, when we look at this P and we find that this A is suitable for us, then we don't need to recalculate. We don't need to look again, because that wouldn't make any sense. We just calculated, how much we need to go for this A, so it doesn't make sense. We should just reuse that computation. So that is pretty much what I did. So here is my get artistic one way, and then here is my get artistic one way, except I flipped the string. And then I also did this tiny optimization. So let me show you this optimization. So if we're looking this way, and we have, let's just say, an A, or I should have also done B's. Yeah, I should have also done B's because we're only looking one way. Dot, B, A, and then finally a P, and then some other things. So what I'm trying to say is we can skip all of this. We can skip it. Why? Because what we only care about is our photographer, because we're only looking for things this way. We don't really care about looking this way. So we can skip all of this until we end up at our first photographer. Hopefully that makes sense. And we can also do from the end. So we can skip anything until we find our first, probably until we find our first B, because we don't care about A's, we don't care about dots. B, or actually we don't really care about P's either, because if we find a P, and we're looking only left to right, then there has to be, in order for it to contribute to a successful artistic photograph, we need to have an A and a B somewhere to the right of it. And if we have never seen a B, then that's not possible. So we can skip the first couple here until we find a P, and we can skip the first couple here until we find a B. Hopefully that makes sense. So that's what I did here. And then I did this thing where I told you. So if I find a P, then I'm gonna find a suitable A, and then if I've already calculated this in my dictionary right here, backdrop right, if I've already calculated this in my dictionary, then I can just skip that computation, and then just add the possibilities. We add something, that we've already calculated. However, if I haven't, then I have to search for B's in the distance between min distance and max distance, which is X and Y. I just renamed them to min distance and max distance because X and Y were confusing. So hopefully that is a good explanation of this problem. So let's go to the next one. The next problem is, this one was easier. It's called Kaiten Zushi. So I think this is optimal. So you're given a list of n dishes. So you're given a list of n dishes, and they have different types. So what you're given actually is the type of the dish. So let's say 1, 2, 3, 3, 2, 1. This is the example given. The thing is, you're also given this number k, which is the number of dishes. Let me see how they explain it. You can eat a dish if it's not one of the previous K dishes. This is your like memory of dishes. So if you eat, and you pretty much have to eat this, there's no choice here. So you get dish 1, you eat it. You get dish 2, you eat it. You get dish 3, you eat it. You get dish 3 again. So the question now, if this K, if you've already eaten in the past K dishes, if you've eaten something of the same type, so if you already just ate a 3, then you can't eat this 3. So you just skip it and you go to the next one. And in the first example, K equals 1. So the dish that you just ate is 3. So you've forgotten by the time you reach this 2, you've forgotten about this dish. And you can eat the 2 again, and you can eat the 1 again. So in this case, the number of dishes you've eaten is 5. However, in the second example, the same types of dishes are given in the same order, and K equals 2. So when you get to 3 here, you don't want to eat the 3. You don't want to eat 3. You don't eat the 3. It's decided for you. You don't eat the 3 because you just ate the 3. And then when you get to the 2, you also don't eat the 2 because K equals 2. So 2 dishes ago, you literally ate a number 2, so you can't eat this. However, this one you can eat, no problem. So the number of dishes you ate here is 4, not 5. Hopefully that makes sense. So how are we going to implement this? I think the easiest way is to, you have a set here of the dishes. So here's my set. So the good thing about sets is that in lookup, whether something is in the set is really is really fast. So let me just show you an example of, well, a set and a deck. Yeah, I think so. Yeah, I think this is optimal. Or technically a queue would work. I think queues and decks have the same efficiency. But anyway, so here's what I'm proposing. You eat dish 1, you add it to the set. So after step 1, your set is number 1, and then your queue or your deck has, so the deck is going to store, so the set is going to store which dishes you have eaten, and then the set is going to store which dishes you have eaten, and the queue is going to store which dishes in the order you ate them. So the thing is, like, when you in this example, right, when you get to the 1, right, I mean, you did eat the 1 in the beginning, but you've eaten the 2 and the 3, and your memory is 2. So by the time you get to this 1, you've pushed the 1 out. Hopefully if that makes sense. So you ate the 1, you ate the 2, you ate the 3, and then by the time you get to this 1, you've pushed this 1 out because K equals 2, your memory is 2. So when you ate this 1, then you ate the 1. Then when you ate the 2, you ate the 2. And then when you ate the 3, you forgot about the 1. So then when you get to this later one, your 1 isn't in your memory anymore, so you can eat it again. So that is how I'm propositioning that we have a set of the dishes that we ate, and then also when we eat a new dish, we have to, if our memory is big enough, if our memory is too full already, we kick out the last dish that we ate a long time ago, and now we forget about it. So we kick out the 1. So to put this into practice in this example, in the first step, we eat the 1, and our deck is, or our queue is just a list of like 1. And then in the second step, here we eat 2 dishes, and this is still small enough. It still fits into our memory. And then our deck is 1, 2. And then when we eat the next, so sets are ordered, and it's very quick to see if something is in a set, which is why I'm using a set here. So when we get a new dish, we check first to see if it's in our set already, and that's a super quick operation. So it's probably like 01 probably. So right, so now we got to the 3, and we're gonna eat it. Why we can eat it? Because it's not in our previous 1 and 2. So here we ate and we have to kick out the 1 because our memory is only that big. So we kick out the 1, we have the 2 and the 3, and then in our deck we have the 2 and the 3. So in our deck not only stores the so why do we keep the set? So it's super fast lookup, right? Why do we keep the deck? So we have a history of which plates we ate. So we can kick out the 1 we didn't need. So the set is unordered, so we can't we can't keep a history of that. But with the dec, we can kick out the 1 and add the 3 onto the end. Right? Makes sense? So yeah, that's pretty much the problem. I think it's very straightforward. So here it is. If dish not in dishes, so that's our set. Then we eat it. Then we add it to our dishes. We add it to our order. And if we have too many dishes in our memory, then we remove the oldest one, and we also remove it from our set. Very straightforward. Okay, let me see. What else is there here? Rotary lock. I think this one is quite easy as well. So here we have our rotary lock. Yeah, I don't even think it's even. I think it's so easy. I don't think it's even worth talking about. So let's go to uniform integers. So for uniform integers, I don't have the cleanest solution, but basically we want to see the difference, the number of so what is a uniform integer? A uniform integer is an integer where all of the digits have the same, where all the digits have the same digit, or they're the same. So all of these are uniform numbers. This is a uniform number, this is a uniform number, this is a uniform number, etc. It's a very straightforward concept. So the question that is asked is how many uniform numbers are there between two numbers that are given to us? Let's say 75 and 300 is the example. So how do we go about doing this? Well, probably the most efficient method is from the 77. So this starts with 77. So you can probably tell that the next uniform number possible between these two, so this is the lower bound, this is the upper bound, so a uniform number has to be bigger than this and smaller than this. We're trying to count the number of uniform numbers between these two. So the next uniform number is 77. Very straightforward, right? We took this first digit and we kind of plastered it to the end so that it becomes uniform, right? So if this instead were 79, I think we would still probably have to try this 77 and then check if 77 is greater than 79. And if it isn't, then we can't add it to our set. However, in this case, 77 is greater than 75, so we can count this 77. So this is our starting point, 77, and then so the thing about these uniform numbers is it's really important to consider how big these integers are. What I mean by that is if they are really far apart, let's just say 75, and instead of 300, let's just say like 30,000. So how do we count the number of uniform integers between these two? Well, first of all, there's some uniform integers with 2 digits. Right, and looking at this example, it's 77, 88, 99. But there's also some uniform numbers between these two with 3 digits. Among those, 111, 222, ... I mean, all of them really, up to 99. And the same thing with 4 digits, and the same thing with 5 digits, and the same thing with 6 digits. So if looking at this, you can already see the pattern that is forming. So when you look at uniform numbers, there is this special case right here where you're looking at the uniform numbers that are between this and the next sort of, let's just say like 100. So it's between 77 and 100. And then you're also looking at the uniform numbers between 10,000 and 30,000. So the thing that you have to know about uniform numbers is that it's super easy to calculate the number of uniform numbers between, let's just say, 1,000 and 10,000. So how do we do this? There are exactly 9. Right, 1111, 2222, ... Like literally every single uniform number that has length 4 is in this range, right? So if we're able to subdivide the problem into, let's say, uniform integers between 75 to 100, which in this case is 3, and then 100 to 1000, which in this case is 9, and then 1000 to 10,000, which is again 9 because it follows the same pattern, and then so on until we hit 10,000. Yeah, I mean, we're already at 10,000. So 10,000 to 30,000, there are 2 here. So you can see these sort of like, so there's from the left and from the right, we have to look at it carefully, which ones are actually in there. But the ones between these ranges of like 10 to the next power of 10, it's always 9 because all of them are in there. So Yeah, knowing this is super easy. So you just come up with a way to calculate the number of uniform integers here, 3. Then you find a way to calculate the number of uniform integers here, which is 2. And then this 9 is, and then the ones, so this, let's say that the number of digits in 75 is 2, and the number of digits in 30,000 is 5. So basically, right, you take this 5 minus 2, you get 3. So how many ranges did we have to, how many 9s did we have to add? We had to add 2 9s here. And then this is proportional. So the number of 9s we have to add is proportional to the distance between the length of these two input numbers. So just knowing all of this, we know that the factor to subtract is 1, and then we end up with 2. So 2 times 9 plus the number between 75 and 300, which is 3, plus the number between 10,000 and 30,000, which is 2. So now there is a special case when the length of the first number, length of A, is the same as length of B. And what I mean by that is, like, let's say we have 4 and then 9. So you can't just look at the numbers. So if you try to apply the same thing, where you say, oh, I'm gonna start at so what I did here, right? I looked at 75 and I try to find the next one, and I went all the way up to the range, right? So I try to find the next one, which is 77, 88, 99. So if we try to apply the same strategy here, we start at 4. When it's one digit, all of them are uniform numbers. So looking at the next uniform number is 4, 5, 6, 7, 8, 9. And then starting here, the strategy I told you was we start and we look for the next lowest uniform number, which is in this case 9, and then we go down 7, 6, 5, 4. So this is super bad. Why? Because we're not only are we double counting, we're also not. So if we try to add these, if we try to apply the same strategy where we just add these two together and add some number of 9s from here, from this kind of calculation, times the distance between them. I mean, basically this is not going to work. Because these two numbers, they overlap with each other, and you also need to consider these numbers, are they actually smaller than, or are they actually bigger than this first number? Because they're the uniform integers are in the same range here, since the length of these two numbers is the same. They have the same number of digits. Therefore, this is a special case. I think since there are only 10 integers, it's super easy, right? We just consider only we only look at these 10 integers, right? So very straightforward. Okay, I think those are all the problems that I want to present. I hope you enjoyed that, and I will see you. Oh my god, my camera's not at all. I'll see you in the next one. Thank you.